Jai Hind viewers, welcome to AKGC Digital School. My name is Pankaj Singh, Faculty of IT Department. Today I am going to deliver my video lecture on a topic of Booth algorithm. Okay, that is a topic of second unit. So before starting Booth algorithm, I give here a brief introduction about Booth algorithm. What is Booth algorithm, why we use it, and where it is work in our computer architecture. So first of all, about the introduction, Booth algorithm was developed by Andrew Donald Booth in 1950s in his research of London in 1950s. Okay, that is the introduction about the inventor who invented, and that is mostly used in a computer architecture part where we perform multiplication. So in a multiplication part, multiplication is possible in cases like when we have a number like 5 into 2, answer will be 10. For a unsigned number, there is no problem, we can use any approach, or we can say traditional approach to perform multiplication. But the case arises when there is a signed number like 5 is minus and 2 is positive. Result will be minus 10. Or in another case, 5 into minus 2, the result will be minus 10. Or maybe both cases are negative. So such type of calculation will be complicated by a traditional approach, or we can say the traditional approach will not able to sort out all these problem in a binary form. So what we have to do, we consider Booth algorithm in which the signed number is easily calculated and the number of iterations is reduced as compared to the traditional method. So before going to the Booth algorithm, I here highlight the main point of Booth algorithm. Booth algorithm treat positive and negative 2's complement operand uniformly, because as we know, in a negative number we use 1 to represent negative on a MSB bit and 0 for a positive bit. But when we perform multiplication by traditional method, we keep this concept in mind that the MSB is 1 or 0. But in case of Booth algorithm, that is not required. It is consider both the cases uniformly. So how it will done and how it will go, I will explain it with the help of example. So here it is a brief introduction about, or we can say some theoretical concept about Booth algorithm. As in all multiplication scheme, Booth algorithm require examination of multiplier bit and shifting of the partial product. Prior to the shifting, the multiplicand may be added to the partial product. As we know that the final product of any multiplication will come after adding the number of partial product, and that's depend on the number of iterations that perform, and the iterations directly dependent on type of size of multiplier. It is of 2 bit, 3 bit or 4 bit, the number of iteration will remain same. The multiplicand is added to the partial product upon encountering the first 0, and the partial product does not change when the multiplier bit is identical to the previous multiplier bit. All these theory will conclude into a flowchart that give the overview how the multiplication will perform using Booth algorithm. So now we will take the flowchart. In this flowchart, as we seen, we store the multiplicand and multiplier bit in two different registers, and we will take a empty register, and if we talk about consideration the place where all such operations will perform, that's known as accumulator. As we know, in machine the calculation is performed in accumulator and the value is stored in a registers. So for example, if we talk about if we take an example of multiplication 5 into 4, here 5 is a multiplicand and it is multiplier. Okay, and the value of multiplicand is stored in a BR register, B abbreviation and R stand for register. Likewise, multiplier is stored in a Q register, QR register, and we will take a empty register. We can say it AC or AR. Which one is convenient? So I will consider it as a AR, but it is actually accumulator register where all calculations initially perform and final result will store. So in this algorithm, what is the main advantage? It can perform uniformly on the 4 cases. What are these 4 cases? First case is both multiplicand and multiplier are positive. Means like plus 5 into plus 4. Second case is multiplicand is negative and multiplier is positive. Third case is multiplicand is positive but multiplier is negative. And fourth case is both multiplicand and multiplier are negative. So what will be the final product? It is 20. That will be minus 20. That will be also minus 20. And that is plus 20. So if we use a traditional approach, we keep in mind the sign of the multiplicand and multiplier. But when we apply this method, we don't require to keep in mind the sign of the multiplicand or multiplier. It will consider all bits in a uniform manner. So take the flowchart. First, we will store the value of multiplicand in BR, multiplier in QR. Keep the accumulator register AR empty, or we can say at a 0 state. By default, the value of Qn plus 1, or we can say it is Qn minus 1. That is the mode of consideration, how to will judge these values from left side or right side, and the sequence counter value at n. So the deciding parameter in this algorithm, that is Qn and Qn minus 1, or we can say Qn plus 1. Here we consider the bits of these two values of Q register. If the value of these two bits is 0, 0 and 1, 1, we will perform the arithmetic right shift and decrease the counter 1 and check their value. If it is 0, we will terminate the our iterations. If it is in number, then we will go to the same step and repeat it until the value is 0. And if the value of Qn minus 1 is 1, 0, then we will perform accumulated ends to AC minus BR. But how do we write minus BR? That is AC plus 1's complement of BR plus 1. And if the value of Qn minus 1 is 0, 1, then we perform AC plus BR. Very simple. After that, in both the cases, it will go to the next step with the arithmetic right shift and then decrease one counter value and check again if it is 0, and otherwise repeat the iteration until the value is 0. So now take the proper example that will helpful to understand how these algorithms will work. So now we will take the same example as I quote in their different modes. I will take here 5 into 4. Okay. So we will store the value of 5 in a register BR and 4 in a QR. So before storing these values, we first calculate their magnitude value. What is the magnitude value of 4 in a binary? That is 1, 0, 0. What is the value of 5? That is 1, 0, 1. Because we are performing both multiplication, so we will add one sign bit, so that will be easy to understand the value of multiplier or multiplicand is negative or positive. we will add here plus 1 sign bit in both cases. So the final will be 0 1 0 1 and it is 0 1 0 0. Now store this value into a register QR and it is into a BR like this. Okay. Now take a empty register, that is AC or AR of the same size. So, and the measure value that is required, how many iterations or up to which step we will perform the iterations, that is very simple. Value of QR equal to count value. So what will be the count? It is of 4. Okay, that is the basic presentation of any values of a Booth algorithm. If we go like this way, it is very easy to calculate the final outcome and number of iterations and their different terminologies that are used in a algorithm. And now we will put all these algorithm in a single location like this. Okay, initial, write down, make a table like this. Initial values. First write down count. Okay, here AR, QR, Q naught or Q n minus 1 or remark. Okay, like this. Make a straight line. Put these values from the above calculated values. Here count value is 4. AR, that is 4 times 0. What is QR? 0 1 0 0. And what is initial value? And what is initial value of Q naught or Qn minus 1? That is by default 0, and we have to calculate this value and make the pair of these two values, and that will helpful to understand what will be the final outcome and iterations. So let us start. Drop down these values on a step 1 like this, 4 0 1 0 0 dash 0, and keep the value of BR at the top of AR, so that we will keep in mind what is its value, that is 0 1 0 1. So in this case, to make the pair of these two bits Q naught or Qn minus 1, we will look at the backward, or we can say the upper value will derive like this, so that we will know how it is come or from where place it come. So the combination is 0 0. As we know that there are 4 cases: 0 0, 1 1 and 0 1 1 0. What we will do in this case? Arithmetic right shift and C tends to n minus 1. Count को एक कम कर देंगे. Like that. Now come to this. When we put values here, so the combination is 0 0. So the what operation will perform here? That is arithmetic right shift. Okay. When we perform arithmetic right shift, there is a property of arithmetic right shift. The shifting bit will move right, and at the MSP location, most significant bit will generate what it is previously. Like, what mean I here to say that if here 0, the 0 will generate at a place of the next value when we shift it right. Let's see, 0 0 0, this 0 move to there, 0 0 1 0 dash, and this 0 will remove. Here vacuum, so we will generate MSB bit 0. make a count value 1 lower, count value here 3. Again drop down these values dash 0. We will again go to the previous step, that will give the value of Q naught. The combination will again 0 0. So what we will perform here? ARS, arithmetic right shift. What arithmetic right shift is? When we shift the values of AR and QR together, it will shift to the right and this position is vacant, and again we will see the previous MSB value. If MSB is 0, we will generate 0, or if MSB is 1, we will generate 1. So I am writing here directly the MSB bit here, and it will move there 0 0 1, here dash 0, C tends to n minus 1. Now the count value is 2. We will again drop down the values. So now we will take the previous value to make the pair of, here is 1. The combination is 1 0. What we have to do in this case? AC tends to AC minus BR. So we perform minus BR in a 2's complement number by making the complement of one of number and plus 1. So we perform here AC tends to AC plus BR plus 1. What is the value of BR here? That is 0 1 0 1. That is BR. Make the complement of BR, that will be 1 0 1 0, and add 1 1 0 1 1. We add these values in a AR 1 0 1 1. When we perform addition, the final outcome like this 0 0 0 1 1 0. If we remember in a flow chart, we will again go to the arithmetic right shift, then make the counter value minus 1 and check if it is 0, terminate the loop, otherwise repeat the iterations. So now we will perform here arithmetic right shift. When we shift towards right, what I said earlier, the MSB bit will generate. So what is MSB? That is 1. So 1 will again generate 1 0 1, and this one shifted to there 1 0 0 0 dash 1, C tends to n minus 1. So now the count value is 1. Again drop down these values 1 1 0 1 1 0 0 0 dash 1, and the previous value is here 0. Make the combination of 0 1. At the combination of 0 1, we perform AC plus BR. AC tends to AC plus BR. So when we perform this operation, again here we use the actual value of BR 0 1 0 1. 1 1 plus 0 1 0 1, and the 1 1 0 and 1, and like that we will discard the remaining value. The final outcome will come like this. I will take here and when we perform arithmetic right shift, it will move towards this. And the final outcome is this 1 2 4 8 16, sorry 2 4 8 16, sorry, that will shift here, and the final value is 20. So by this method we will calculate the value of 5 into 4, that is 20, and that is the binary of 20. So thank you. We will meet in a next video for Booth division.